So in our last video, we defined what's meant by electron affinity. In this one, what I'd like to do is to look at periodic trends in electron affinity. And you're going to see that they have a lot in common with the periodic trends for ionization energy, which is not surprising since, as you learned, electron affinity and ionization energies largely correspond to the same chemical process. So what I have here at the top of this particular page is a figure showing us electron affinity as a function of atomic number. So this is what happens to the electron affinity as we march through all of the elements in the periodic table. And so the first thing I'd like to do is just look at it for a couple of minutes.
Oops. Stop for a minute. We are getting more mic.
Oh.
Yet, so please,
all right, well, we'll just move me.
You haven't written anything yet, have you?
No.
Okay, I think someone's stopping for you.
Yeah, that's fine. You want to try it again?
Yeah, it seems better. Sorry.
Okay.
From the top.
All right. So in this video, we're going to look at the periodic trends in electron affinity. Now, in the last video that you learned that electron affinity corresponds to the energy associated with adding an electron to an atom, which is in a sense the opposite of the energy you need to put into a system to take an electron away. So there are natural relationships between ionization energy and electron affinity that are also reflected in the periodic properties of electron affinity. So in order to look at the periodic properties, what I've done here at the top of this page is to create a figure of electron affinity as a function of atomic number. So as we march through the periodic table from hydrogen to helium to lithium to beryllium, this figure shows us what happens to the electron affinity. So here at hydrogen, we have an electron affinity of about 0.75 eV. At helium, it then drops to 0. Lithium, it comes back up again. Beryllium, again, drops down about to 0. Boron, carbon, nitrogen, oxygen, et cetera, et cetera. So when we're learning periodic trends, we typically look what happens left to right across the periodic table and what happens top to bottom within a group in the periodic table. So conveniently for us here at the top are our friends, the halogens, fluorine, chlorine, bromine, iodine. And you can see that actually there's very little change within a group in the periodic table as we move from the top to the bottom. So there's basically no trend in electron affinity from top to bottom within a single group. You see that's true in the halogens. That's also true if we look at these alkali metals, hydrogen, lithium, sodium, etc. There's really not very much change as we move from the top to the bottom within a single group in the periodic table. This is arguably quite different from what we've seen for some of the other periodic properties. However, as we look at what happens from left to right across the periodic table, we see again a trend. As we go from potassium through to bromine, the alkali metal in the third period, through to the halogen in the fourth period, we see that electron affinity increases from left to right across the periodic table, just like ionization energy, but in a sense for a different meaning. Right? In the case of ionization energy, what this meant is you need to put more energy into a system to take an electron away from a halogen than you need to put into the system to take an electron away from the alkali metal in the same period. But this increase in electron affinity means that you gain more energy when you put an electron into a halogen than when you put an electron into an alkali metal. So within each period, the halogen has the highest electron affinity, which we see. And this is actually a really easy argument. It's basically just a result of the increase in effective nuclear charge, the same as the increase that we see in ionization energies. But the trend within a period is relatively complicated, right? We see all these elements that have electron affinities that are almost 0. And so the question is why? Why do these elements have no interest at all in adding an electron? And the answer you probably already know, since we've already been talking about ionization energy, is that we have to look at the specific ground state electron configurations of these atoms in order to understand really what's going on. So the first one that I'd like to look at is the electron affinity of nitrogen. So if we just go back up here for a moment, lithium, beryllium, boron, carbon, nitrogen is one of these elements that has a ground state, has an electron affinity of basically 0. And so let's see if we can relate this back to the ground state electron configuration of nitrogen. The ground state electron configuration of nitrogen is the helium closed shell, the 1s, the full 2s2, and then it's a group 5 element. So there are actually 3 electrons in the 2p atomic orbitals. And so what you see is nitrogen has half-filled 2p atomic orbitals. And so if another electron were to be added to a nitrogen, it would have to occupy a half-filled p orbital, meaning it would have to pay the pairing energy penalty. So there's no actual energy released when an additional electron is added to nitrogen, because that would disrupt this half-filled status of the atom. If we look at another example, we could consider that beryllium also has an electron affinity of almost 0. And so why is that? Well, beryllium is the alkali earth metal in the second period. So it has a helium closed shell configuration, and then a closed 2s atomic orbital with 2 electrons in it. So addition of an electron to a beryllium atom would go into the 2p atomic orbital. But we know the 2p atomic orbital is actually higher in energy than the 2s, noticeably so in beryllium, so that it doesn't release energy. So adding an electron to the 2p of beryllium is not energetically favorable. So the electron affinity is not positive. And so finally, we can also use what we know of the general trends in electron affinity to be able to predict whether the electron affinity of one element is larger or smaller than another. And so in this particular problem, I'm asking you about the electron affinity of gallium relative to that of germanium. These are 2 elements that are important in the semiconductor industry. Gallium is in the family 3A in the 4th period, so that it is a closed argon shell followed by a 4s2 3p1. I'm going to ignore those d electrons for the moment. They don't actually play a role since germanium and gallium are both main group elements. Argon is immediately adjacent to, germanium is immediately adjacent to gallium on the periodic table. It's in group 4A under carbon and silicon. So it has a ground state electron configuration in which the open vacancies are in the 4p orbitals. Sorry, those should say 4, not 3. So there's no real obvious reason that either of these elements should be resistant to gaining an electron. The new electron is going to go into a partially filled 4p orbital in both cases. So we would expect these 2 elements to follow the normal trend that electron affinity increases from left to right because of, why does it increase? Increased effective nuclear charge. Everything comes back to ground state electron configuration, size of orbitals, or effective nuclear charge. So in this case, it's not ground state electron configuration, it's effective nuclear charge. So the effective nuclear charge of germanium is higher than gallium. So we expect the electron affinity of gallium to be lower than the electron affinity of germanium. The germanium will release more energy as a result of the electron interacting with the higher effective nuclear charge. So to just sum all of this up, electron affinity is closely related to ionization energy. Its trends, just like those of ionization energy, are driven by effective nuclear charge and ground state electron configuration. So when you're thinking about electron affinity, you want to make your predictions in the same way that you would for ionization energies.